Hello, everybody. So in this video, I'll be covering aromaticity. Now, before we get into some questions, what I want to do first is cover the concept, understand how to approach questions that involve conjugation, understanding aromatic, non-aromatic, and anti-aromatic, and some frost circles. So let's begin. Okay, so the first slide that I have for you guys is, do you understand what a fully conjugated compound is? Now, I have an example that I drew out for you. It's a 5-carbon chain. And the most, I guess, simple version I can tell you is look for double, single, double, single. That's when you know a molecule is fully conjugated. So that's what I have over here. I have double, then I have single, then I have double, and then I have single. So this molecule is fully conjugated. Now I'm going to show you a molecule that is not fully conjugated. So what I'm going to do is draw a 5-carbon chain. And the last 2 of the carbons, I'm going to add 2 double bonds, which are the terminal carbons. And if we do a double, single, double, let's try it out for this one. Double, single, single, double. So it's not going to be considered fully conjugated. Okay. So those are your 2 examples. Now what we're going to do is we're going to determine if the left compound and the right compound are fully conjugated. Okay, so let's start with the left compound. So in the left compound, what stands out is the oxygen, the nitrogen, and what they both have is a double bond and a lone pair. So one thing you do not want to count, especially on this compound, are the lone pairs. And the reason why, since we already have these double bonds, they are already in the ring system. So that's why we do not count the lone pairs at all. So if you already see an atom that has a double bond and a lone pair, only count the double bond. Make your life 10 times more easier. So now we're going to check if it's fully conjugated. We have double, single, double, single, double, and single. So yes, this compound is fully conjugated. Okay. Now let's try out the compound on the right. Now, this compound is a little different. We have an oxygen with 2 lone pairs, and we also have a carbon with a positive charge. So since we have an oxygen with 2 lone pairs, what we can do is do resonance. We want to see if we do the resonance structure, are we going to create a fully conjugated compound? So let's try that out right now. We're going to start with the lone pair on the left side, and we're going to move those electrons so that the final destination of the double bond can stabilize the positive charge of that carbon atom. And where that positive charge ends up is going to be on an oxygen. So let's double check our work. We have double, single, double, single, double, and single. So yes, we are fully conjugated. For right now, I will come back into multiple ring systems. I promise. I'll probably get towards the end. But what I want to do first is show you guys this chart. And this chart is really going to explain about Huck's rule and just in a more simpler way. So what I did here for you is I gave you all the numbers of the pi electrons that are aromatic and anti-aromatic. So when you use this chart, what you want to do is whatever compound they give you, you want to double check your work. Are you fully conjugated? And if you are fully conjugated, that's a yes. So you want to count the total number of pi electrons they give you. Magic numbers for aromatic is 2, 6, 10, 14, 18. For anti-aromatic is 4, 8, 12, and 16. So I drew out 3 examples here for you. One that's aromatic, which is a benzene ring. Fully conjugated, it's a beautiful conjugation. Total number of pi electrons, you count each double bond as 2. So 2, 4, 6. We have a total of 6 pi electrons. Next thing, we'll do the anti-aromatic. I think this one's pretty cool. Now for anti-aromatic, yes, we are fully conjugated, and I'll show you by doing the resin structure.